today my talk is on elimination, and I see this as a great way to connect both GI health and detoxification. That word elimination can be a bit nebulous in its usage, but for this purpose, I think that there's a really great way to describe that term as a way overall to basically look at all the different ways the GI is in support of removing things from our body, which is a very essential procedure that it needs to do. So we have a lot of slides in here, and it's more than I can go through in extreme detail. So I'm going to be speeding through a couple of these and really just try to hammer down a few of the very key details on this. But then also make sure that, since the slides will be out there for anyone who wants to go back, review them, and try to pull out a little bit more information there, since I do think that this is such a great way to build off of some of the earlier presentations and try to connect all of this stuff together. So for elimination, we know it's part of that 3 phases of detoxification. We have our entry points for potentially harmful substances to make their way into the body via the lungs, the skin, or external barriers, and then also the external barrier of the GI tract. The GI tract is also a very unique pathway because of its very key usage as part of the elimination from cells. Detoxification processes go through the liver, and I'm going to let a few of the additional lectures cover more of that phase 1, phase 2 activation conjugation step. But we're going to focus today primarily on that phase 3 during this talk. So the way that things are eliminated from both cells as well, so this elimination occurs both from cells as well as in the from the body itself via either stool or urinary pathways as a primary location, but also then you have some lung and skin based too. Now, the key players in elimination, those external barriers, making sure that they are functioning properly and that they are adequately maintaining things out. So there was a lot of talk in the previous session about the gut barrier integrity. So maintaining that is going to be very important for that barrier to be functioning properly. Same with skin health, but also really focusing on that GI health. So the gut's luminal pH is important. The presence or absence of food, that actually affects things. And then the different digestive enzymes, the production of bile acids. Bile is a very important compound that our body makes for elimination, specifically coming from the GI tract, as well motility, so the passage of time of stool in the body, and then the permeability of that of those different barriers, specifically the GI permeability. Then efficient metabolic detoxification, making sure that all the right nutrients are there to facilitate that, but also just dietary components have some specific things. So those high fiber plants, they aid in helping with elimination and bowel movements, but also there are some materials that really do drive some of these activities by interacting with the potentially problematic substances that are also consumed. Then we have another class of things. They fall more into that supplement category as adsorbent materials. And this is not to be confused with absorbent. So adsorbent are the materials that are capable of trapping certain substances to or within their pores, thus shielding them from interactions in a biological or chemical system. Basically, this is a way that the bioaccessibility of something can be changed, and therefore those substances, they don't get integrated directly into that material, but they rather get just trapped within it in some form or fashion to where it's prevented from interacting further, but it doesn't chemically change that substance. It stays the same usually. Oh, let's see. Hold on. Let me make sure I got this. So for focusing on nutrition and elimination GI health, the body has to sift through everything. These can be beneficial things, but also potentially harmful things. So we get exposure to a lot of these things that come through the diet and have to undergo that xenobiotic metabolism, be it water that we can, or drinks that we consume, as well as food. And then our bodily defenses, they result from, they can come from driving rapid elimination or um, driving rapid elimination or uh, just helping to maintain maintain general um, sorry, hold on, my view got changed. I'm going to fix this super quick. uh, okay, I couldn't see the slide, sorry. And so the bodily defenses, they result from avoiding exposure as well as driving that rapid elimination. So things can be either interacted directly, taken up in the body, but they could also be just avoiding any kind of interaction in general by driving that rapid elimination. Some substances can actually support this, and for a lot of our elimination pathways, they may, under certain conditions, actually need that additional support. So for the gastrointestinal tract, there's a lot of different sources of these compounds. So they can be chemical, biological, synthetic, and the common sources can be byproducts of metabolism in the GI, as well as metabolic detox byproducts. So these things that are coming out via that phase 3 elimination. In the diet, they can be byproducts of cooking. So heterocyclic amines, PAHs, those things that occur when thermal processing hits food. They can create these harmful compounds that then our body has to undergo detoxification to change. But those can be interacted with in the GI tract with various other things. Our diet is also a source of heavy metals. So as standards continue to improve across the world, and this is a target of continual improvement, trying to lower and lower the exposure from these heavy metals, it's actually very hard to just limit that exposure entirely. Lead is just ubiquitous in the environment at this point, and it's something that we're just going to, for the foreseeable future, constantly be exposed to, particularly because a lot of those very beneficial foods for us also that come from the earth, they do wind up containing certain amounts of heavy metals. So just knowing what kind of exposures you're dealing with, and then if you have an occupational setting for patients that exposes them further, or their diet may be exposing them further, looking at ways that elimination can be supported for them. Then microbial sources. So fungi can produce mycotoxins, and then bacteria, they can produce exotoxins. So those are going to be things that can expose to the GI tract, either through their generation in the GI tract or by their generation in a food that is then ingested into the GI tract. So that can happen one of or either of those two ways. The GI environment contains of this upper and lower sections. They have relatively different profiles to them. Acid or a very acidic environment in the upper GI, but also the production of a lot of these key components like bile produced in the liver, stored in the gallbladder. And then in the lower GI, you have a lot of this is where all the absorption happens in the small intestine and the large intestine. And as you move throughout the large intestine, the concentration of microbes increases and increases. There's a lot of detoxification enzymes that are actually found in the lower GI tract, with a lot of these exporter proteins found at the tips of the villi in the intestine to help export them out of that organ. pH is going to be driven these changes in the upper GI from hydrochloric acid production. So maintaining proper pH is important there. And then pH in the lower GI is oftentimes maintained by a lot of the organic acids that are produced from a lot of the microbes that call that region home. And this pH changes is important because non-ionized forms of the weak bases and acids, these things they're more rapidly absorbed in that ionized form. So it can affect the way that things are taken up in the body. And certain minerals, such as the beneficial ones and the negative ones, those are actually, their absorption can be pH dependent, changing via the presence or absence of these organic acids. So the lower GI, usually you're looking for that slightly acidic pH in a general setting. And for the bile acids, bile production, we produce around 700 milliliters of bile a day, and it acts as this detergent to help mediate the more liquid environment of the GI tract with a lot of the fat-soluble compounds that our body needs to absorb, both the vitamins that are fat soluble as well as fatty acids that are used for energy. But then you also get a lot of these potentially problematic substances that are brought into the bloodstream via and transported through via these fat or these emulsifiers as bile acid. So bile is very unique because of our body's enterohepatic recirculation processes. So what's produced in the liver and ultimately reaches the lower GI tract is regulated, the biosynthesis, by a feedback mechanism where the bile can ultimately be reabsorbed and recirculated, controlling a lot of that presence and the demand for biosynthesis from cholesterol in the liver. So this ultimately leads to about 95% of that bile being absorbed in the terminal lumen from a normal healthy individual, with about 5% of it by weight being removed via the feces each day. Too little bile can be problematic for malabsorption, but also too much bile can be problematic in leading to negative side effects such as diarrhea. There's also a tie for certain bile overproductions in various IBS-D conditions where individuals with excess bile, it winds up stimulating excess defecation in the stool. There's a lot of interactions with microbes in bile. It can be antimicrobial to many of them, but also some are able to conjugate, digest it, and tolerate it very well. So probiotics, usually for a good one, you need it to be able to be bile tolerant. Xenobiotics, so these potentially harmful substances that often go through these detoxification pathways, those can actually be reabsorbed as part of this enterohepatic recirculation if they are of that fat-soluble nature and can reach the lower GI. certain substances certain substances can actually help facilitate the removal of bile and bile salts. So fibers, beets, okra, cauliflower, some of these show a very moderate ability to bind bile salts. Then there's some much stronger drugs that are designed to do this that are very, very efficient and have been used for a number of different reasons for trying to ensure that removal. But then there's also in the supplement realm that's adsorbent materials. Activated charcoal and clinoptilolite, those have both shown the ability to be able to bind bile very efficiently in this intestinal environment. Fiber itself is going to be something that it's very underconsumed, as was being described in the previous talk, but it's something that we definitely are not getting enough of in the diet. And the fiber that we are ultimately getting is usually going to be this nice mixture of insoluble and soluble. They both kind of serve different purposes, but fiber is important for that production of short chain fatty acids, also driving bowel movements. And what we've seen in studies that look at fiber as part of a detoxification of xenobiotics and removal of that from the body, in those clinical trials, the addition of fiber has been supportive of ensuring additional removal of those materials from the GI. So it's a very important component to make sure is being incorporated into any individual concerned about that sort of issue. Collinsonia root is a good example of an herb that is a root that has a very high amount of fiber. It's about 45% fiber on average, and that's been used traditionally for its elimination support. Then what we also have tied with all this is the gut barrier. The gut barrier itself, with those 4 distinct layers: the microbial layer, the chemical barrier, so that's made up of mucins and all sorts of different secretions that coat and line the physical barrier that's made up of epithelial cells, goblet cells, Paneth cells, intertwined with these tight junction proteins. and those ultimately separate that microbial layer, which can be very helpful for us in a number of different ways. But keeping that and the immunological barrier separated helps to regulate our body's immune response, where so much of that immune system resides in the gut. Maintaining this barrier is important for being able to respond to all sorts of external threats in that semi-internal external environment of the lower GI. And within this this barrier, what we have are all sorts of potentials for that to actually break down. And when you do have a breakdown of that barrier, it is possible for an individual to have what's called hyperpermeability. Commonly referred to, leaky gut has been used a lot in some more practitioner spaces, but this is where you get increased absorption of things being able to move through the GI and stimulate some of these immune responses. This has been tied to a lot of that chronic inflammatory response, low-grade inflammation occurring in the GI, and it's a very snowball effect. So you have some things that start to break down. So you have a dysbiosis occurring. It causes more of this, and the breakdown the immune response creates more damage, allowing more of it to break. So it just winds up being something where you get a flare up and it's tough to control. So this can be also a problem as part of exposure to toxic compounds, because it makes them potentially more available and more, once you're also removing these things, if that is not shorn up, then you have more ability to re-expose via the lower GI tract for things that would have been otherwise removed. Certain conditions have been associated with this. If you look at these percentages here for these various conditions, they range from the study identified some of the highest associated conditions to having also increased intestinal hyperpermeability in those patients. So a few of them, the autoimmune conditions, specific dermatitis had a very high increased permeability, diabetes with chronic liver disease, as well you have some of the additional digestive ones, irritable bowel syndrome, Crohn's, ulcerative colitis. Those all have some of these ties, but it is important, since those aren't at 100%, to be able to pair functional tests for practitioners to be able to see how necessarily problematic that is. Looking at microbes, the populations are important. So when you have an imbalance of symbionts to pathobionts, you can wind up in a state of dysbiosis. And then there's also the presence of these temporary colonizers. The beneficial temporary colonizers you'd think of as probiotics, but the problematic ones would be a lot of your classic pathogens. Many of them produce their own biological toxins that ultimately cause a lot of their negative symptoms associated. So looking at microbes as a potential source, but also a source of compounds exposures, but also a supportive agent for elimination, you have direct toxin generation that can occur via some of these microbes. So yeast produce these mycotoxins. There's some literature around how candida, certain problems can is it a mycotoxin? Is it a different toxin that's not quite as large as a mycotoxin? Candida does have some affiliations with that. But then the very classic ones would be those aflatoxins that do wind up occurring on food. Then you have the bacterial ones, Clostridia difficile and enterotoxigenic E. coli. Those can directly produce these exotoxins in the lower GI tract. And then the components of these cells, those can drive a lot of that inflammatory response. So just the cell layer of a lot of these problematic species have what's called a lipopolysaccharide that drives inflammatory responses. There can be indirect toxin generation as well. So certain things that have been removed via that three-phase detoxification and brought into the GI tract for elimination, sometimes those can be reconjugated by microbes and ultimately re-return into the body. So you can have some of that re-exposure occur via that. So also the increased availability of a particular toxin. So maybe it was packaged within a plant fiber somewhere, and your body actually didn't break that down enough in the first pass, reaches the lower GI tract where it would be bound for removal via the stool. But for various, if you have efficient enough microbes, sometimes they can increase that exposure. They can also change via their metabolism some of these compounds that may not be problematic into something problematic. So you have something there to consider just with these microbes, in that they're not always going to be beneficial, but they can induce some of these potential issues in the body. Then you have detoxification support. So It's not all bad. It's not all good. Microbes are a little bit of a double-edged sword always. But detoxification support that they do provide, they can directly bind some of these toxic compounds just by their physical structures. So these can be either live or dead microbes, and that's been shown in probiotic studies, a lot of it with Lactobacillus plantarum, both live and dead as its postbiotic form, can bind some heavy metals. And then there can be certain detoxification in the same way that it could make something more available. It can make something detoxified. This can occur inside the body, but also outside as part of food. We use a lot of fermentation procedures as part of detoxification, but you just do it before you consume it. So historically, this has been done in procedures. You look in areas of Africa where cassava flour has very high levels of cyanide. When you ferment that, you can actually break down and remove that cyanide to where it's no longer an issue. So you can change the via fermentation some of the availability of toxic components. Prebiotics can also do some of this either via direct interactions, but also indirect ones by inducing growth of beneficial species or driving the production of certain metabolites that can also have influence here. So that can be directly on potential pathogens, but also on compounds themselves and things. So prebiotics are a really unique area going forward because they have the ability to change the general full population in the body. A novel prebiotic compound that's been touted a number of times through this talk already are these human milk oligosaccharides. The most prevalent human milk oligosaccharide, first, these have been identified in human milk, is 2-fucosilactose, and these have been outlined as important components of an infant diet as part of breast milk. It's what drives a lot of the prebiotic generation in infants, so driving the growth of bifidobacteria. As well, it acts as an extension of the mother's immune system to the infant, where based off the very unique structure of these components of these human milk oligosaccharides, they can actually act as microbial decoys for their binding to an intestinal cell. I'm sorry, the slides are not appearing to be advancing at this point. Oh, here we go. Okay, so the human milk oligosaccharide mechanism here, you can see that based off the structure, some of these surface-bound sugars, but also these sugars, monosaccharides that act as binding sites. You basically are using environmental microbes as virulence factors that allow them to initiate their colonization against themselves. So they confuse these 2FL molecules, the fucose on the terminal sugar, as a binding site, and then they no longer become available to bind to either the mucous membrane or the mucin floating around coating the cells, as well as the surface sugars on the cells themselves. This also has shown to have structural ligand binding potential towards certain exotoxins, but it's part of why you see in those breastfed infants that it is you see less diarrhea episodes in these breastfed infants than formula-fed ones. So a lot of the Campylobacters and the E. coli, rotavirus, those can confuse these human milk oligosaccharides for binding sites and ultimately be removed without causing their initial infections. So it's a really unique prebiotic compound that is now able to be synthesized, or not synthesized, derived from a fermentation procedure and utilized in dietary supplements for both adults and for children. Okay, let's see. I got a couple of slides move forward. Adsorbent compounds, adsorbent materials, some of the most common ones: activated charcoal, diatomaceous earth. I've heard a lot lately about humic fulvic acid, these activated carbons coming from a lot of very recent fermented soils, and then also bentonite clays. Each of these is a different flavor for adsorbent materials. They provide a little bit different activity, each of them, but not all of them work very well as a supplement. Certain ones have some some differences and some potential problems that make them difficult to work with. But you do see a few of them that we've really identified as having some standout capabilities for being able to be delivered to humans for consumption, just based off general safety, as well an ability to work with, and a very selective binding capacity. We've really focused on this Clinoptilolite for this possibility. It's something that has a new dietary ingredient notification that was submitted and ultimately not objected to, which meant that it was able to be utilized under certain conditions in dietary supplements very well. So that's unique also in having quite a lot of clinical data present. It has a high stability in pH, which is a very unique aspect when you compare it to something like bentonite clay, where it is very, very good at being an absorbent, but under certain pHs that can wind up, certain compounds can be re-released or have to rebind. Also, something like bentonite can't be purified in the same sense. So a lot of the natural components, since these are earth materials, it's very hard to remove the excess heavy metals that they bring with them in the earth. So something like zeolite can be purified while retaining a lot of its positive benefits. And then chlorella is a unique one because it is a former living thing as an algae, and it has some emerging science behind it, and it is a very unique source of chlorophyll. Otherwise, some of the other ones, those other ones, they don't also have a lot of clinical backing behind their long-term use in people. So something like activated charcoal has a lot of anti-poisoning research around it, but it doesn't necessarily have that same level of research when it comes to the chronic usage for like lower dosages. Cracked cell wall chlorella, it has some. It's demonstrated the ability to increase detoxification of heterocyclic citric aromatic hydrocarbons. It also has a direct adsorbent capability where it can bind some of these heavy metals. It's also shown the ability to bind some synthetic dyes, so it gets used industrially quite a bit. But in these studies based in humans for chlorella being used to detoxify these are dietary components that are introduced via cooking, thermal processing of meats mostly. And what they saw, what you see with feeding these chlorellas at a relatively low dose, you can wind up reducing the hypermethylation in genes and these metabolizing factors for these various hydrocarbons, and increase the removal of them from the diet, so the direct removal and elimination from stool. Clinoptilolite, it's unique. It's this material from volcanic ash that's been weathered in a marine environment, so that saltwater environment, over millions of years, and it creates this very unique honeycomb structure material that is part of the zeolite family of compounds. But as far as zeolites go, it's probably the best one when it comes to being used as a dietary supplement. Certain other ones, like something like aroneite, that winds up having a different crystalline structure, not that honeycomb structure, and that elongated structure actually can make it potentially harmful to humans. So the clinoptilolite is very unique in that it has a very very tolerable structure for humans, and it's been used clinically abroad. It has a different classification. It's not classified as a dietary supplement. It gets classified as a medical device. So it has a pretty heavy basis of research for its usage. And it's uniquely able to be purified. So certain compounds or certain groups are using these zeolites and purifying them via patented processes to deliver very highly adsorbent clinoptilolites that are very pure. They can remove a lot of those impurities that you get as a natural compound. It then can be micronized. A lot of purified clinoptilolites, they'll be in the range of like about 3 microns with pore diameters. So in those honeycombs, the pores within them that increase that surface area of them greatly, they can be around 0.4 nanometers, so much smaller. And these have very good thermal and pH stability, so they can be sterilized well without breaking down, contrary to something like bentonite, and they can be purified very well to not deliver things like, when you look at something like fulvic acid, that can actually deliver thorium as part of it. So it's hard to clean that up with it retaining its activity if you keep it close to that structure that works. And then like diatomaceous earth has an arsenic leaking issue, and bentonite clay can have very high levels of naturally found heavy metals in it that under different pHs may not be as stable. So the way that clinoptilolite works is it has three forms of binding. The first one I'm going to describe is called ion exchange. In these honeycomb structures at an active site, you can have environmental cations. This is where, when you go through a purified one that's utilized a process to prepare it, it can be loaded with calcium ions. So these calcium ions can be at the center, so that when an environmental cation that has an affinity that matches what clinoptilolite can grab, it can wind up displacing one of these calcium ions. And those calcium ions go into the solution, and the environmental cations are then trapped, where they are then easily removed and they're shielded from interactions in the body. So if you look at the affinity pattern, it has a very high affinity towards lead, cadmium, some additional ones. It has a high affinity for cesium. It also winds up having an affinity for mercury. Some of the other non-problematic metals that it has affinities for, the good thing about them is, for the most part, these are all more on the macro scale that they'd be present in foods. So you can make a tiny dent in, say, something like calcium or calcium or copper or something. But that tiny dent that you make, it's very different than making the tiny dent in something like lead, where very small amounts, very low levels of it is very problematic for an individual. The second type of adsorption action is binding, and there's two different binding types. There's one that can occur within the structure of the clinoptilolite itself. So this is where you see a lot of the bacterial exotoxins and mycotoxins binding. There's a net negative charge that these wind up binding and being trapped within these pores. And then in the larger molecules, where you can have some of these larger agglomerates form, where the clinoptilolite has a net negative charge on the outside of it, it can surround it and then decrease that bioaccessibility there by limiting the amount of interactions that can have. That's how it binds cholesterol. That's how it binds bile. The way that it binds bile ultimately has been demonstrated in some in vitro models. Where bile is added in presence of certain other toxic compounds, like a bacterial exotoxin, and it's been demonstrated that clinoptilolite has a very high affinity for that bile binding. Oh, here we go. Okay, so sorry, things jumped ahead again. So in that bile binding, what we see is that it is able to induce that binding very effectively at a very low dose that's relevant for individuals. You also see that in clinical studies with lipid binding, clinoptilolite has been used to reduce the absorption of dietary cholesterol at higher doses. This graph here that shows all these different clinical studies that have been used, you see some of that dyslipidemia treatments that it's been used for occur at 9 and 6 grams, so a few of those higher dosages, but then clinoptilolite's been tested at very low dosages for heavy metal removals, so down to as low as 0.24 grams per day. Then moving up higher, as low as 1.8 grams per day have been used to reduce excessive bowel movements and help with loose stools. Then you start seeing gut barrier benefits at that about 1.85 grams per day. And then a very, very unique study at about 2 grams per day of lead uptake. So I'm going to jump ahead to that lead uptake study really quick, but there are other additional studies here, and my presentation does list those clinical studies in that previous slide if you want to go back and review those yourselves. So in this study with lead, a radio-labeled lead in this study, it was just recently published in 2021 in Nature's Scientific Reports. So this was a very, very high profile study to come out on something like clinoptilolite, and it was very well done. A purified clinoptilolite was utilized at 2 doses, 2 and 4 grams per day. And it was done in individuals in a pharmacokinetic trial where you give them a certain amount of a radio-labeled lead. So in this case, it was 2.5 micrograms of lead per day, which is under what's allowed in the country that this was done in. So it's far below the safety standards of the excess amounts. But so looking at, as far as a chronic usage, how can you look at something like a regular dietary exposure of lead and how you might be able to, with ingesting clinoptilolite, reduce that uptake. limit the bioaccessibility, ultimately decrease that bioavailability by doing so. And what they saw in this study was that in the placebo group, that lead absorption from a lead drink wound up just shooting up right away, and ultimately reaching that final plateau, and then just staying in the bloodstream as well as the urine. When you looked at either of the clinoptilolite treatments, you saw such a large reduction in this. It was over 95% reduction in both of them. Very similar, not statistically significant in its difference between the two, demonstrating that there's an ability for this to bind basically on what was available as part of that. So the clinoptilolite itself was very efficient at binding it, and this probably signified that it even works at much lower doses than that 2 grams, which was the lower limit. Okay. And then for tight junctions, we know that adsorbent compounds, when you feed these in animal trials where you stress the GI barrier, you can lower the inflammation, you can decrease the permeability of the GI tract. And looking at the mechanisms for how these absorbent containing mixtures do that, it's usually driven by a combination of protecting the barrier. So by that adsorbent action, protecting it from damage, and then also allowing for enhanced mucosal barrier repair functions to be observed. So that's really cool. And then when you take it into the human model, there's a study that was done at 1.85 grams per day in an exercise-induced model. So you can stress people really hard with a lot of exercise, and it actually makes their gut have a higher intestinal permeability amount. And then what you can do is give them you can give them this clinoptilolite at that 1.85 grams per day. And what that'll do is reduce the amount of zonulin, which is a biomarker for stool in the stool for intestinal permeability. You can reduce that to the point where you can see that this clinoptilolite is able to induce that gut barrier protection. It's also been demonstrated in people with irritable bowel syndrome, who about 30% of them usually have this intestinal hyperpermeability. Statistically significant changes in alpha antitrypsin, which is a protein that circulates in our body, in the blood, that can, when in leaky gut, make its way into the stool, and it resists digestion, so you can measure it. Clinoptilolite 3 grams per day showed that it was able to reduce that level of permeability. And you also see that you can see some mucosal protection in times when stress has been induced with a treatment of NSAIDs. You can see that at about 3 grams per day. Looking at that purified clinoptilolite in cells, you can also see this from interactions with exotoxins. So Clostridia difficile toxins, they can induce in these cell monolayers hyperpermeability very greatly. You see that box that shows that the width between those cell junctions increases. And then when you do that in the presence of clinoptilolite in a digestive model, so bile salts are there, other things are there, you can greatly reduce that. And then also in this integrity model, you can see with an electrical resistance assay that when you have those Clostridia difficile toxins, it reduces the permeability integrity greatly. And ultimately, when you have the clinoptilolite, it protects from that. So a very unique material. The source matters, so make sure it is a purified clinoptilolite that is being given, that has undergone the safety and regulatory standards. And there's going to be all kinds of ways that you can utilize these absorbents, and there are different points of interaction in the body. So this can be in people who have normal elimination pathways, but also in people who have improper ones. So they might have constipation and slower stool transit, increasing the amount of time for potentially harmful substances to be absorbed. Absorbents can interact with it at the beginning as well, all the way through that longer track, affecting the GI barrier. You can wind up looking at that as a way to limit the excess uptake via leaky gut. And then also microbial generated toxins. Aflatoxins bind very well to clinoptilolite and other adsorbents. So this is where you can have that interaction occur directly. There's a number of different ways. Also, the enterohepatic recirculation. You can bind bile, help initiate some of its removal. Very important when patients are undergoing something specific like a digestive, like a detoxification procedure. So are they trying to actually actively remove things and inducing that? You can wind up utilizing an adsorbent to make sure that you're shoring up that phase 3 elimination process. identifying patients for this, you can ultimately look at it at times when you think that those patients are also going to be getting additional exposure. So are they going to a new environment? Are they going to have hyperpermeability? You can test this clinically with a few of those ones, as well as a lactulose mannitol test that we were talking about, but also just if they have any of those chronic health conditions. And wrapping it all up, pairing together the nutritional support, so fiber sources, beets, okra, collinsonia root, great. Adsorbents, purified clinoptilolite, chlorella, and then microbiome support with probiotics, also botanicals, postbiotics, and then bile, support the bile generation, bile flow, so certain cholagogues that help its moving, but also those bile clearing agents, most of which I described just a minute ago. Okay, I think I'm over time. I was trying to go through it fast. I apologize if I was moving too fast to here, but thank you very much for listening to my talk. And we can always have you guys direct questions through Megan, and we can try to get back to you on certain things.